control the speed? Last class we have discussed by varying the armature resistance. Okay, so by varying the armature resistance, what we have achieved? We have just controlled the speed. And the second method is the speed control by varying the field current. Okay, so for varying the field current, first thing what we have to do, we have field circuit where resistance is we are going to vary it. Okay, for that externally we are going to add a resistance in series. I will explain it further what we are going to do for in the name itself, that is by varying the field current. So in order to vary the field current, what we are going to change? We are going to change the resistance of the field winding. Okay, and the next what is, which is constant over here, means the armature voltage is constant. What is varying? Field current is varying. At the time who is constant? Armature voltage is constant. Whereas while varying the armature, the vice versa. Okay, so if it is varying the armature resistance, means their field current will be constant, armature voltage is varying. Okay, two things will happen in varying armature resistance. First case, yesterday I taught you one case, right? Their field current is constant, armature voltage is varied. Here field current is varied, armature voltage is constant. Okay, so by varying the name itself, by varying armature resistance means who is varying? Armature voltage is varied. Okay, field current, other field current is constant. By varying field current means field circuit resistance can be varied. Armature voltage is constant. That we are not going to change. Only the thing we are going to change is the field current here. In armature, only thing we are going to change is the armature voltage there. Clear? These two things. Basically, you clear with that. So first point, what we are going to do? We are going to change the value of resistance in the field circuit. Next, what is going to be kept constant? Armature side I am not going to touch. That is kept as constant. Armature voltage is constant. Field current has to be varied. How it can be varied? First, we know the relationship. If phi changes, what happens? We know the relationship. That is N is proportional to what? The supply voltage to the phi. Okay. So if the flux producing the field, that is if it is changes, which also changes, the speed changes. Okay. So that is the basic thing you know. Now I told you that is the external resistance connected in series. What we are going to do in the field winding, we are going to connect a resistance there. So listen, the next step. What we are going to do, we are going to change the resistance of the field winding, right? For that, what we are going to do, we are going to connect the external resistance in series to that particular field winding. That is how we will be changing the field circuit resistance. Okay, externally you are connecting a field circuit resistance over there. Okay, so after connecting that, what will happen means the flux will start to decrease. So if the flux will start to decrease, means what happens? Automatically the speed will increases. Anyhow, we want to control the speed. Either I have to increase the speed or else I have to decrease the speed. Both the cases are said to be what? Speed control. You are controlling the speed. Either to decrease it or else to increase. If a motor is running at a very fast rate, you have to control it. Means what you have to do? You have to, if the operation is said to be speed control. Either to increase the speed or else to decrease the speed. Okay. So now here what is happening after adding external resistance to the circuit? What is happening there? The flux is getting decreases. So then the speed is getting increased there. Okay. Which means you are controlling the speed. Which is you are anyway changing that any mode of speed. Either you are decreasing it or increasing it. The real meaning is you are controlling the speed. Okay. So the speed control is in your hand. Like this. So the speed is what happening? It is increasing. What is the reason for that increasing in speed? Means we have added a resistance in series to the field winding, right? So what the current that flows to the field winding, the current field current what happening? It is decreasing. Okay. So resistance if we have added means what happens to the current? You know that in the fan regulator itself there are 3 points. Okay, which means one resistance, two resistance, three resistance. When the value of your resistance is getting increases, your current flow is getting what happens? Decreases. Okay, so that is how. Okay, so what is happening? The field current is getting increases, and your speed is now field current getting increases. Flux is decreases. Likewise, flux is also decreasing. So speed is what happening? Increasing. So speed has to be increased about a rate, right? That rate is said to be what? It is increasing about the base value. Okay, so that base value is to be explained in this. Keep it in mind. First, what do you have done? We have varying the field circuits current. Okay, so what is kept constant? Armature voltage is kept constant. Okay, the basic thing, the flux changes, speed changes. So I have to change the flux. To change the flux, what I am going to do? I am adding an external resistance in series to the field winding. So if I add an external resistance in series to the field winding, sorry, I have to say if the flux is basic thing, flux changes, speed changes. Okay, so externally you are adding a resistance in series to the field winding. So flux is what happening? Flux is getting decreases, where speed is getting increases. What is the reason for that? The decrease in the flux, the field current is also getting decreases. So speed is increases above the base value. Okay, so this thing, after this what you have to see means the graph. Okay, that is under two conditions, either at the no load condition or under the load condition. Okay, two conditions. Take this as that is here first basically. Okay, n naught, that is initial condition. Both the cases are we are taking it in no load. There is no load over here. Under no load condition, how the speed will be? That is speed divided by k, some constant. The current I don't know. Okay, Ia or we are changing here If. The current I don't know. That's as k into the flux phi. Sorry, division. Okay, so k into phi. Okay, now what happening? I am adding the external resistance. So when on the no load speed you will get what happens? It changes. I have marked it as what? N naught dash. Okay, so here n naught dash. Okay, so under no load, if my motor is operating, what is happening? It is constant. So you can see the response over here. So it is constant. Okay, I haven't changed anything. Next, what we are doing? I am adding a resistance. What is happening? My speed first initially increases. After that, it is decreases. I already told you that what is happening? Speed will get increases. Okay, so speed is getting increases. Okay, at that point, see in this here over during the speed of the no load condition, what is happening means my speed will be comparatively low here, but torque how it will be means higher. Okay, here straight opposite. Here the speed will be high, torque will be low. Okay, with respect to the armature current we have seen. Okay, so next, likewise here it is a no load speed. Next well as after adding the resistance, what is the change in the speed? That is equal to V by N into that flux. If the flux changes means after adding the resistance, the flux will be changes like phi 1. Okay, phi suffix 1. I have marked the change in fluxes. How? We have marked that it as the change in fluxes phi suffix 1. The real flux which exists in the machine is phi before the controlling of speed. Okay, can you differentiate these two things? Next what you have to consider, these two flux. The real flux while the machine is running, after adding the resistance and speed can be controlled. At that time the flux is phi 1. How it will be means the relation between these two means the real flux will be greater than the flux phi 1. Can you imagine now the real flux is, if it is greater than the phi 1 means first the real flux which is in the value. For example, take the flux is 1.5. Okay, at that time the speed of the motor, just imagine. Okay, at that time this speed of the motor is 1500. Okay, so now what I am going to do? I am going to decrease the flux further. Okay, so if I decrease the flux, what will be my speed? If I decrease the flux, what will be my speed? It increases. Can you imagine now? The speed is getting controlled. This how. Okay, so the real flux, there is a value. At that time, the motor is running at a speed. Okay, after adding external resistance to the field circuit, what is happening? The flux changes to phi 1. That is what happening? Decreasing. Okay, so flux decreases. In base value, there is a speed that is getting increased. Okay, as I already told you, either you are decreasing the speed or increasing the speed, you are controlling the speed. Clear now? So now that is the change in the relation between is the real flux that is greater than what? The flux phi 1. That is the change in flux after adding the resistance in series to the field circuit. Okay, and next, so this kind of applications is suitable for where means it is suitable for a constant load torque. Wherever we require motor to be at a constant torque to be maintained, we will be applying this type of speed control over there. Okay, and the next thing is, so now who comes in role now? Load torque. Okay, this load torque will be equal to the armature torque. That can be taken as some constant K into I suffix A, that is armature current. Okay, and now this load torque will be if it is constant. Okay, this load said to be what? Constant load torque, right? So if it is constant means what is happening? The fluxes reduces to phi 1. Okay, that is how. Okay, the load torque can be applied in low constant load torque. So the load torque is constant means flux phi can be reduces to phi 1. Can you mingle everything? Flux phi is reducing to phi 1. Can be suitable for what? Load torque. Okay, at constant load torque. Clear? So this is how the response. Now torque or else we can response of the power also. Okay, two things we are saying. Constant torque as well as power relationship with the respect to speed. With respect to speed we are seeing. Okay, so how it will be. During now our resistance is added. So this control is what? By varying the field resistance. So named as resistance control. Okay, how the speed initially? It is constant. After till the flux is phi. After the resistance added, what happens? What happens? Speed is flux is reducing. Okay, so reduce the torque. What happening there? Here it is high torque to belongs to where? Low torque. Okay, that is how the response. Now, usually I told you one point that it is base speed is what happening. The speed will be above the base speed. Can you imagine? Up to this is the base speed. After this, what is happening? Speed is above the base speed. It's not reducing. You should not see that this now. Speed with respect to speed is how it is increasing. See the x-axis. The x-axis is only speed. What is happening? Above the base speed, the speed is increasing. Okay. This is for what? Torque explanation. And above the base. After this, you have to see the x-axis. Above the base value, the speed is increasing. Clear? This is how the varying of speed control by varying the field. Next lesson, losses in the DC machine. Okay, overall we will be saying it as overall power losses in the DC machine. So it is how much means first the power loss that happens in the armature, overall losses. Okay, that is the total power loss is equal to what are the losses being inside happening. That is power losses of which will happen in the armature winding. I will describe power loss in the power loss. Okay, P loss. That is power loss in armature winding. Along with that, power losses in the there is poles over there. Between two poles, interpoles there will be some losses. Next, compensating windings. What we have done to control the speed? We have added a compensated winding. Compensating to compensate what have added a resistance. Such kind of windings may cause some losses. Okay, we are adding that is compensating windings. Power loss due to compensating windings. Then the power loss due to field coils. Okay, next the power losses that is due to the presence of brushes in there. Okay, it will be having some resistance. So next the power losses due to the field windings. Okay, so these overall losses will take place inside a DC machine. That is said to be the overall total power losses in the DC machine. So describe these things. That is PAW is the power loss in armature winding and as well as interpoles winding, compensating windings, field coils, and then what it is? Brushes as well as field winding. Okay, and now copper loss. Another losses will happen. Okay, so that is said to be what? Copper loss. Copper loss, other name is we will be saying it as I square R losses. Okay, why this is happening means there is the container armature, there is a container I square R. Here we have seen the power loss, copper loss. Okay, so P is equal to I square, that is power loss. Okay, I square R power, right? Okay, the losses in power only we are seeing. Okay, so what I square R losses we can say that is copper loss also. Why we are saying that means conductor. Okay, armature is a conductor. What we have done? We have done the windings with the copper wire. Okay, so that it might have some losses are there. Okay, so that is said to be what? Copper loss, or we will be saying it as I square R loss due to the presence of resistance in the copper wire which is wound in the conductor and armature conductor or which is wound in the conductors. Okay, and now that is categorized as three. One is, as I said, armature, copper loss. Armature, the winding is what? Copper. What we have done in the poles have wounded with field winding. Field winding is also made of what? Copper. Okay, so that is categorized as armature, copper loss. brush also there will be, as I told you, there will be some resistance. Okay, these three things will come under the copper losses. Okay, and now first, yeah, in that also this brush will stand alone. Okay, we will be studying it together, but the brush won't be coming to the total copper losses. Just copper losses is happening due to the presence of copper wire which is wound in the armature conductor as well as the field winding. Field winding is also made up of copper wire which is wound in the poles. Clear? Now two copper losses, one is happening in the armature winding, another one is happening in the field winding. So name it as armature copper loss, field copper loss. Clear? So the armature copper loss, as I told, power, that is power loss. Power is what? I square R. Okay, that you know. So the loss of power, copper loss is said to be what? I square. In armature means we will be naming this I suffix A square R suffix A. That is current in the armature resistance. Armature resistance. Next, for field winding. Field winding is connected in two ways. Either we are connecting it in parallel or else we are connecting it in series. Okay. So if the field winding is connected in parallel, if it is a DC shunt motor means the power loss or else the copper loss is said to be what? ISH square or SH because it is connected in shunt. Okay. So if the field winding is connected in series, if it is a DC series motor means the copper loss or else we can say it is the power loss as I suffix SC square or SC. Clear? So now can you tell me both the windings are there? Okay. So for a compound motor, what will be the copper loss then? For a compound motor, there is a field connecting field winding is also there. Series connected winding is also there. Shunt connected winding is also there. So for compound motor type of motors, what is happening? The total copper losses will be the armature winding is there, as well as field winding will be twice. There is in series also there will be a winding, in shunt also. So total copper loss of a DC machine can be named as how? The armature copper loss, that is IA square RA plus the series connected. If it is a compound motor also comes under what division? DC machine. Clear? So we have named as the total copper losses armature copper loss IA square RA plus series, the field winding in series ISC square RAC plus. If it is a compound motor, there will be shunt field winding also ISH square RSH. Okay, because DC compound motor is also comes under what? DC machine. We are seeing the overall losses of the DC machine. Clear up to this? Next to the brush power loss. What is happening? In brush, there will be an inbuilt resistance over there. Because of that, there will be some losses. Okay, that is we know that power P equal to what? V into I. Okay, so this V is what means we are naming it as V suffix dB. The dB means that it is the voltage drop across the brushes. Okay, if there is resistance means what will happen across the resistance? What we have calculated? Voltage, right? So across the resistance, anytime across any element we have to find it means what we have to find out? The voltage across it. Okay. We have to find out what is flowing through the element, what we have to find out? Current. Okay, current will flow through the element. To measure the voltage, we will be taking the across condition because voltage is the potential difference between 2 points. Current is the flow of electrons. Can you identify these two things? So, the brush losses is equal to, we know the power is equal to V into I, and here VDV, that is the voltage drop across the brush as well as the current that flowing through the brush. That type of losses will take place in the brush. Okay. So here, in a motor which is running in a full load condition. Okay. In a full load condition, how much of this armature copper loss will be? It will be about 30 to 40% of the overall total power loss. Clear? If a motor operating in a full load condition, there will be some losses, right? In that particular losses, about 30 to 40% of losses caused by who? Armature copper loss, and about 20 to 30%. That is about 20 to 30% of losses at the full load condition caused by whom means field current loss. Okay. Mechanical losses, and you know what are the terms that is happening mechanically. When a motor is running, what will happen there? There will be friction will be there. Okay, so that is related with friction loss. Okay, next means windage loss. Okay, what is happening? We have multiple windages are there in the mechanically we are connected. So windage losses will be there. And one more thing we will be having mechanical losses, that is we will be saying it as stray loss. Okay, that is S-T-R-A-Y, stray loss. The stray loss will happen in the, it is a mechanical thing. Okay, motor or machine is what? It is mechanically compound. Okay, so that happens what? Friction is a principle that happening. So frictional losses will be there. Next one is windages are there. So windages there will be losses. Next we are naming it as stray loss. Stray loss means both the case of friction loss as well as the iron loss. Machines are made up of what? Iron. While the currents are flowing, what is happening? In iron also there will be some losses, right? So the friction loss as well as the iron loss together is said to be what? Stray loss. Friction loss and iron loss together is said to be stray loss. Okay. If it is asked, define stray loss means what you have to say? The mechanically built a DC machine, the friction loss and the iron loss together on the stray loss. Okay. So the next is the mechanical system. The mechanical running system, the friction loss and the iron loss together is said to be stray loss. Okay. And next thing is some constant losses will also happen. What is a constant loss and what is a variable loss? Iron mechanically it's made, okay, designed motor. This iron piece is what? It's constant. Okay, so that is the things which is happening due to the presence of the constant particle. That is said to be what is constant loss. Okay, so another term is what means variable losses. So variable losses, what is varying there? Flux is varying. Okay. So due to the varying quantities, if suppose the loss is happening, that is said to be what? Variable loss. So in overall, we can say what in losses of a DC machine, we can say it as constant loss. That is due to the mechanical parts plus variable losses. That is due to the flow of flux, voltage, current, whatever the mechanism happening. Overall losses happening both due to the presence of mechanical components as well as the variable components. The total losses can be overall said to be constant losses plus variable losses. Can you differentiate these two? Constant loss is the iron piece which is present here. The screw which is present here. Okay, that is mechanically what are inbuilt, that is constant. Okay, that is designed in the design itself, that is inbuilt, that is constant. The flow of flux, all these things are what happening? It is variable. Both the losses are happening, that is a total loss of a DC machine. Okay, and next is the efficiency. To calculate efficiency, efficiency means what means? That is how the performance of the motor will be, or else how the performance of the machine is. Okay, so that is said to be what? Efficiency. We will be saying it. If you are studying, your output will be what? Efficient manner, which means in a good manner, right? So we have to find out that efficiency of the machine. That is how it has been worked. To calculate the efficiency of the machine, what is the formula? The ratio of output to input. The ratio of output to input, we are calculating in terms of percentage. We are calculating in terms of percentage. So what we have to do? We have to multiply with 100. Efficiency is what? The ratio of output with respect to the input. We are calculating in percentage. So this is the formula for calculating the efficiency of the DC machine. You know what amount of power we are giving. Okay, and you comes to know what is the output power. How to calculate the efficiency? Output divided by input into 100. Okay, here what is happening if I am giving an input? If I am giving an input power, okay, what will comes out? Some will comes out output. What will what is going to remove from there? Some will be removed as losses. Okay, so our input is equal to what? Output minus losses. And what will be the output? Input plus losses. Okay, so input input plus losses of our output. Clear? So if I substitute these two both, the first in the first equation and the second in the second, which means efficiency can be calculated how? In terms of, if I want to calculate the efficiency only in the terms of input, means how I am going to find out? I don't know output. I don't know what is the amount of losses and what is the input I am giving. So if I want to calculate, means in place of output, what I have to substitute?
Input plus loss.
Input plus loss divided by input into 100. And likewise, in terms of output, I have to find out, means what I have to do?
Output by
Efficiency is equal to
output by output minus
output
loss.
divided by
Output minus loss.
output minus loss. In place of, that is
Input.
in place of input, output minus losses into
100.
100. This is how efficiency can be calculated. Efficiency is the performance of a machine. How the performance of the machine can be calculated? The term is said to be what? Efficiency. Efficiency defined as what? It is the ratio between output to the input. Since it is calculated in percentage, we are multiplying with the 100. Okay. So our input is what? Our output, the projected losses. Okay. And our output is what? Both the input and losses. So if we substitute that in, these are the efficiency formula. That is all about your second unit. Okay. First, initially, what we have learned in the second unit, construction of a DC machine. Can you tell me the parts of the construction of the DC machine? Yoke. We have to come from the outer frame. Okay. Yoke. The next is the yoke or frame. You can say this frame also. Next, what is there inside? Pole. Okay. Pole. In pole, there is a pole there. Pole. Shoes there. They are mounted. Field windings there. Along with that, inside who is there? Armature conductor. Next to the armature conductor, armature winding. Armature conductor, armature windings are there. Okay. And next who is there? Commutator. Commutator. Next brushes. Next only shaft rotor. Okay. So describe it. After that, the working principle. You know what has been. I will show you a video, right? So working principle you can able to. Okay. Next, what you have seen? EMF equation. How to derive an EMF equation. How to derive a torque equation. Next, how to control the speed of the motor. Two types of controlling the speed of the motor. One is by varying the armature resistance. To vary armature resistance, field current is kept constant. Okay. Armature voltage is allowed vary. The next method is field resistance varying method. In field resistance varying method, field current is varied, armature voltage is kept constant. Vice versa case. Okay. So after everything we have done with the help of what? Graph. We have covered with the basic equations. Flux, how will be the speed, flux is there, how will be the torque, and if the current I is there, how will be the torque and speed, everything we have calculated. Next thing is, next what we have seen, losses. Okay. So the losses, now total losses, total power losses comes into all the armature winding, field coils, brushes, compensating windings, interpoles, brushes, what is that? Interpoles, everything. Okay. So all the losses together is bring the power loss. After that, what we have explained? Copper loss. What is the copper loss? That is due to the presence of the copper wire in the armature winding as well as the field winding. The presence of copper in the copper part. So that is two. One is armature copper loss, other one is field copper loss. So if it is in a compound motor, both are exist. So total copper loss, how it will be? There is a shunt connected field winding as well as a series connected field winding means how the total loss will be. Because the compound motor is also comes under the DC machine. After that, what we have seen? Efficiency. To calculate the efficiency of the DC machine, how we only have to do the ratio between output to the input into 100. Okay. So if we have to calculate with respect to input alone means here is the formula. Likewise, if we calculate the efficiency with respect to output alone, one of the quantities not known means this you have to solve. That's all about your second unit. One is other two losses. What it is? I have already told you during the working principle. Hysteresis losses and eddy current losses also. Okay. Eddy current losses. Why it is happening? Eddy current losses is due to the there is an electromagnetic principle also inside. What is happening? Faraday's laws of electromagnetic principle. That is main thing. Whenever a current carrying conductor is placed in a magnetic field, there is opposite poles are being built inside winding current carrying conductor is placed in a magnet. There exists what? An EMF is generated, induced there. So due to that, what is happening? Back EMF is producing. Due to that, what is also happening? There are some losses. That loss is said to be what? Eddy current loss. Okay. Eddy current losses cannot be reduced. It cannot be eliminated. Okay. Why? Because means it is that principle will happens. Okay. It is in physics it will happen. Whenever a north pole south pole is there, it's a conductor. Whenever you are placing a two magnet of north pole south pole, if you place a needle, it will react due to the attraction forces. Okay. But eddy current losses can be reduced to some amount by lamination. That is why they have laminated everything. That they are described in the construction. Laminated sheet of silicon, laminated sheet of iron. That's a theory. Okay. So there is a formula for that also. That is for hysteresis losses. That is power loss, right? Hysteresis losses will be saying as the maximum flux density. Maximum flux density to the power 1.6 into frequency into voltage speed. This is how the hysteresis losses will be. And the eddy current losses will be the maximum. See, if your book this proportionally constant is mentioned as A, please write that and make it as proportional. Okay. So next it is as F into V, and here eddy current losses V